Let's talk after class, right? Huh? Your name's on it. Is that what you're asking? Alright, let's go ahead and get started. I know some of us are still working, but don't forget, one, this is an understanding check. It's not your final grade. I will give you feedback on what I see so that you can improve your understanding by the test. When are we testing? Tuesday, right? Y'all's exam is on Thursday, so we got to test Tuesday. Cannot believe it's already that time. Thanks, Lexi.
I just hate math, sorry.
You're doing so well in my class. I don't understand how you can say that.
You can be good at something and not like it.
I don't know. I like the stuff I'm good at.
I'm good at funny.
Nathan doesn't like math, but he's good at it.
Anyways, so two quick things. One, 3 out of the 14 of us turned in our graphic organizer yesterday. At least I only think I got Lexi's, DJ's, and Gracie's. If you have yours today, okay, please get that out, put it on your desk, because I am going to give you feedback and return it to you. But if I collect it on Monday, I cannot help you before Tuesday, right? If you don't have it ready to turn in today, then my suggestion would be to email it to me. Email me a scan of it so that I can give you feedback and send it back to you. If you're giving it to me right now, then I will give you feedback. I'll put feedback on there during my second block planning so that you can come by and get it during third block or fourth block. So I would take advantage of that, huh? It was just the front of that page, yes ma'am. Because remember, I took off all the transformations. Okay, beyond that, I do want to point out for those of y'all who did turn in their graphic organizers, I went beyond just asking questions. This time I was intentional about identifying the days and the pages that each of these terms were heavily discussed, so that when you look at it, you can go deeper or add extra detail. If you improve your graphic organizer, maybe you had space on there that you could add extra stuff in, or you get a separate sheet of paper out and write more information down as you reflect on what you're supposed to know, and you turn it on your on test day, I will honor that and you can earn a higher grade. So some of us may want to take advantage of that. Some of us need to get that understanding check in, or the graphic organizer in. Remember, it's designed to help you reflect upon what you know to help you prepare and learn better. But let's get started with today. As I said, if you have your graphic organizer, I'll come by and collect it maybe at the end of class or something like that. So, getting started with today. Here's our agenda. We started yesterday with the exponential properties. Today we're going to use that to help us learn about the logarithmic properties, because we need some of these logarithmic properties to solve exponential and logarithmic equations. And the nice thing is, the logarithmic properties make a lot of sense if you understand the exponential properties we did yesterday. What am I referring to? When I say exponential, I mean power properties. What were the power properties we discussed? The quotient power property, that looks like this one right here. Well, before we jump into that, what is the quotient power rule? You subtract the exponents, right? You said the zero power rule? What is the zero power rule? Anything raised to the zero is 1, right? That's the zero power property or rule. What other power properties do we look at?
Quotient power, quotient rule of power.
Say that one more time.
Quotient rule of power.
Quotient, we already did that one, right? When you divide, that's a quotient, and that's when you subtract the exponents. What else? Power to a power, which that one's not on here, but remember that's if I have 3 squared raised to the 5th. When I have a power raised to a power, what am I going to do?
You're going to do the 3 to, you're going to repeat multiply 3 to the second 5 times.
So, remember, if you go back, there we go, right? If you go to the basics, right, 3 squared to the 5th is 3 squared multiplied 5 times. But I could recognize, I'm just going to multiply those powers, right? That's going to be 10 3's being multiplied. Huh?
Do you know what page?
M3-185. Okay? And then there's one that we're missing, the product power rule. When we multiply powers with the same base, what do? Add their exponents, right? Those are the power rules. There's one other one, but we're not going to stress about it too much. Oh, by the way, I did mean to tell you this, because Kyle was asking about a study guide. So as I said, I've been keeping better track with this graphic organizer, exactly what pages each of these concepts are on. I'm going in and filling that out on the graphic organizers that we've had in the past on this 9 weeks. And so I'm actually going to email that out, hopefully early or middle of the day tomorrow, so that you know what pages to be looking at in the textbook and what notes and what days we covered some of those concepts to help you study better for the exam. So that would be your study guide.
Are you doing exemptions?
I mean, yes, but I'm not looking at exemptions until next week because
Yeah.
we have a test on Tuesday.
You know, they won't let you check out, like, they have papers, like, checking everything now.
What?
Like, they're checking your, like, how many times you've checked out, and if you've checked out too many times, they won't let you check out anymore.
Interesting, I did not know that. Okay, so what I want to talk about here really quickly is there are these different power rules. We just talked through them a little bit. But we need to recognize that we can actually have multiple power rules happening at the same time. That's what I want to discuss. But nothing changes, right? When I look right here at A, I have x to the 5th being multiplied by x squared being multiplied by 1x. Well, first off, what is 4 times 6? 24? By the way, we know what page we're on, right?
Yes.
Just flip it one page, make sure you take these notes. So there's 24 for 4 times 6. And then it'd be x to what power?
8.
How'd you get 8?
Oh, wait, I think you're right.
I would say 8.
It's so, you
Okay.
gonna add them. You add
Supposed to add them, right?
So.
So we've got 5 and 2 and
14.
that's understood to be 1, right?
Oh, yeah, it's gonna be 14. Okay.
How'd you get 14?
I don't know.
We don't add any 6, because it's a Y.
Oh,
Remember, yeah, that's why.
Oh, okay, so you want to add an extra, so it's gonna be 8. Yeah. 8.
Looking at Gracie, we have 5 and 2, and that's understood to be,
Oh, I didn't see
1.
that
okay? And then y to what power?
7.
7, okay? What rules do we have at play in B? Quotient? Anything else?
Are you gonna use the rule where you gotta divide, you gotta subtract? The rules in the first
That-
one?
Say again.
What was the rules in the first one?
Okay, what are the rules that we were using here? What are we doing?
Power.
They're all powers, but product, because what is a product? We are multiplying. A product is multiplication, right? So that would be a product rule of powers.
You're using 2 of them.
Yes, ma'am. What two are we using?
Power to power and product rule of power.
On B?
No, A.
Remember, a power to a power is when everything is raised to an exponent, right? Do I have anything around one of those expressions, raising it to another power?
I don't know, so which one did you add?
Oh, product.
Oh,
That's product. And so I want to pause for a second because y'all are looking at it almost backwards in this case. Look at the name, product rule of powers. What is a product? Multiplication. So because I am multiplying, I add the exponents. You're trying to go backwards. You're trying to say, oh, I added the exponent, so what is the rule? No. What is the rule? I'm multiplying, so it's a product rule. That's why I'm adding the exponents.
So the B also product
Do we also have a product there? Yes, right? We have a product rule. What else? And what's a division? Another word for division is? And quotient, right? Does it matter which one you do first? Nope. But, so you choose what's easier for you. Lexi, did you start to say something?
What is the one called when you have the same base and you add the exponents?
You're thinking about it, so you're doing kind of what LaShana was thinking about. Start with the definition of the product rule, right? Product is when we're multiplying. What did we do with our exponents?
Oh, no, add.
We added them. The product rule, right? A to the x times a to the y. When I multiply numbers with the same base, I add their exponents. That's the product rule.
Okay.
Now, I will point out, does anyone know why that's the product rule? No, we just kind of accepted it because we were told to do it in Algebra 1. Okay.
Algebra 1, I was handed a book and said, write the number.
Hey, what does it mean to do x cubed?
X times itself.
X times itself how many times?
3.
3 times.
Yeah.
Times x times. Hey, how many x's do I have? Remember, an exponent is repeated multiplication, right? So aren't I increasing the number of x's by 2? What mathematical operation is an increase? Adding. That's why I'm adding the exponents, because I'm increasing the number of x's. So when they have the same base and I'm multiplying, I'm increasing how many numbers I have. Okay? In a similar way, for this quotient rule, if you want to make this note here, if I have x to the 5th divided by x to the 3rd, let's go 7th. If I have x to the 7th divided by x to the 3rd, what am I repeatedly doing because of those exponents? No. Because the exponent, I'm repeatedly multiplying. Divided by how many x's? Now I want you to notice, what is x divided by x? It's 1. What is this x divided by x? This x divided by x. Notice I'm not increasing my number of x's, I am decreasing because division is the inverse of multiplication. How many x's did I decrease it by? So how many x's am I left with? That's why we're subtracting. I'm decreasing by that number of x's, so I'm going to subtract. Okay? And we actually already looked at the idea of power to a power when LaShannon mentioned that it would be like 3 squared times 3 squared times 3 squared. I'm repeatedly multiplying, so I had 5 sets of 2, which is why I need 10 of them. Alright, big thing for me, again, you can approach it any way. I might, in this case, multiply first. Don't forget that's understood to be divided by 1, because when I multiply fractions, I multiply the numerators, I multiply the denominators. So 42 times an understood 1 there is 42. What's m to the 5th times m to the 4th? M to the 9th. Remember, I'm increasing the number of m's, I'm multiplying. It's a product rule. That's when I add. Into the 5th. When I am multiplying, I'm increasing, I'm adding.
Yeah, but once you get the 6m,
Well, remember, that's 1 times 6m to the 6 into the 5th. Remember, I'm not done yet. Right? What's 42 divided by 6? 7, right? 42 divided by 6 is 7. M to the 9th divided by m to the 6th. Remember, I'm decreasing my number of m's. So, m to the 3rd, right? I'm decreasing it by 6. And then n to the... n to the 0, or what is n to the 0? 1. Notice, what is n to the 5th divided by n to the 5th? So there's multiple ways to approach it that way. But this way I can also show the idea of a 0 power rule, because anything to the 0 is understood to be 1.
So we can add that rule to the time.
Well, oh yeah, you could add that 0 power rule if you're using it in that case. Yeah. And then finally on C, what rule are we going to use? Power to a power. Now we'll point out with a number, a coefficient like this, it's just negative 3 raised to the 5th. Okay, don't make it more complicated than that. But then it'd be x to what power? How'd you get 35?
Wait, how you get that?
The what?
What you get?
The negative 3 to the 5th?
Yeah.
Well, notice this whole thing is being raised to the 5th, isn't it?
When are you pound?
So isn't the negative 3 being raised to the 5th as well? Like the negative 3 is inside of that, so negative 3 is being raised to the 5th.
When are you pound rule? So that'll be negative 15.
Well, no, because remember it's negative 3 to the 5th, not negative 3 times 5, but it'd be power to a power rule, so it'd be x to what? 35. And I might even write it for a second like 7 times 5, but power to a power, I'm going to multiply those exponents, right? Times y to the 15, and that's coming from 3 times 5. I'm breaking it down here. Negative 3 to the 5th, I would have to check it on a calculator, but I'm pretty sure it's negative 243. X to the 35th, y to the 15th. And so I use my power to a power rule there. So hopefully that's a little bit of a refresher. And then I could use a product rule, I could use a quotient rule, or a zero power rule. Any of that stuff afterwards. What?
How do you get 30 times 5?
Well, Shannon, that's not 3 times 5.
Oh, there it is, she's talking about that experiment.
That's not 3 times 5. It's negative 3 raised to the 5th.
The other one.
I think she talking about
The
where
other
it's
one.
where the y over
You
y.
talking about this?
Yeah.
You just break it
That's
down.
3 times 5.
She said what I did. You said not
She's
3 times
asking
five.
where
I thought you were talking about this. What's 3 times 5?
She don't know where it came from.
Yeah,
Oh.
that's how-
We're raising a power to a power, aren't we?
It's in the equation.
Oh, never mind.
It was y cubed, and then I raised it to the 5th, so it'd be 3 times 5.
Okay.
Sorry, I thought you were talking about this. I was like, no, we don't have 3 times 5. Yes, we have it there. Does that make sense?
Yeah, I was asking why.
Ah, remember, if we raise a power to a power, what do we do with those exponents? Multiply. All right. So here's what I want us to understand. Logarithms are what? Inverses of exponentials. And also when we evaluate a logarithm, we get an exponent, right? So all of those power rules that we just talked about, do you think they might matter for, I don't know, logarithms? Might be connected somehow? Okay, so what we're going to do is we're going to take about 20 minutes or so, maybe just 15. I don't think it should take you too long to look at some of these properties. So let's consider the zero property of powers to develop a corresponding logarithmic property. Write a sentence to summarize the zero property of powers. B to the 0 is equal to 1. Notice that's an algebraic statement. What would be the sentence?
Anything raised to
Anything raised to the 0. Equals 1. That's it. Don't make it more complicated than that. Now we're going to write the zero property of powers in logarithmic form. There's a corresponding logarithmic property called the zero property of logarithms. What would that zero property of logarithms be?
And the rest of that is one.
Okay, hold on a second. Are we dealing with functions right now with f of x? No. Remember, I'm taking this exponential equation and I'm writing it as a what? Logarithm. Log base b. The argument be 1. Because remember, a logarithm always equals an exponent, right? Have we seen that statement before? Log base b of 1 is equal to 0? Yeah? So state the zero property of logarithms in words. So, log base b of 1 is always what? And that's because that 0 is the what for the base b? Exponent, right? So I might include that detail to fully understand this. But log base b of 1 is always the exponent 0. Notice this ties very heavily into the zero property of powers, or the zero power property, however you want to say it. So I'm actually gonna leave this one for y'all to work on in your small groups. I'm gonna look at the next one with you. So this one is where we get into some more complicated stuff in the sense that they show all these diagrams, but it's not nearly as complicated as they're showing it. So let's consider the product rule of powers to derive a corresponding logarithmic property. How would we write a sentence to summarize this product rule of powers? B times n, or B raised to the m times b raised to the n is equal to b raised to the m plus n. How would I explain what that is saying? So when do you add exponents? So when, okay, yeah, when the bases are the same. So anytime the bases are the same, we add exponents?
Yes.
No.
Those bases are the same, we're gonna add?
No.
Okay, so when multiplying, okay, do you know what this entire thing together is called? Starts with a P. Just this part, not the product. Remember, product is multiplication. Think about the name of this rule. Power. When you're talking about the base and the exponent together, you're talking about the power. So when multiplying powers with the same base, right? So y'all were talking correctly about the idea of the base, but we also are dealing with an exponent. So multiplying powers with the same base, what are we going to do? Add the exponents. Okay. So let's think about it this way. Let's say I take a logarithm of both sides. And let's say that so we have b raised to the m times b raised to the n equals b raised to the m plus n. You all good on that? That's from what we did earlier. Okay, so what I'm about to do is just show you the background of why this works. We're going to focus on the rule in a second. And what I'm going to do to make more sense out of this, I'm just going to say, hey, b to the m is equal to, let's say, the number x. I'm going to let b to the n equal the number y. I promise this will make more sense in a second. So I have x times y is equal to b raised to the m plus n. That's what I have now. But let's say I don't want that base. What's the inverse of an exponential? No, ma'am. A logarithm, right? What logarithm would I need to take of both sides? Log base b? Because what do those inverses do since they're the same base? They cancel out. By the way, I would write this down because this will help explain things. Notice then, log base b of x times y is equal to what? M plus n. So notice how this is very tightly connected with what we did with the exponentials. So what we're saying is the product of, or the product rule of logarithms. And I think they even say to use our words in a second. But the product rule of logarithms is here. And there's another way that I can write this. So notice how when we are multiplying inside of, what is this term called? The thing inside of the logarithm? Well, so the x and y are variables, but the name of that thing inside the logarithm is called an argument, right? So when we're multiplying within the argument, what do we end up doing?
Getting the exponent, I guess. Adding.
we're adding the what? The exponents, right? And so we want to remember an exponent is just a logarithm. And so the true product rule, what this comes out to be then is that log base b of x times y is equal to log base b of x plus log base b of y. That's our product rule of logarithms. Notice that's a lot like exponentials. When we are multiplying, we end up adding. Because remember, that is m, and that is n. Right? So what we would end up saying over, well, I'll let you finish writing that, and then we're going to put words to this to make more sense out of it. So when what? How would we describe that statement?
When you have an argument, you add the exponent.
What's happening with the argument? Being multiplied, remember it's a product rule, right? So when multiplying, well, when multiplying within the argument, the logarithm, because remember what is a logarithm? An exponent, right? So when multiplying within the argument, the logarithm can be separated into what? But we're writing it with a log, right? When multiplying within the argument, the logarithm can be separated into a sum of logarithms. Right? When multiplying within the argument, the logarithm can be separated into a sum of those logarithms. Now the base needs to stay the same. Logarithms with the same base. Let's say it that way. Okay. Now, we could save time by just going over the other two together, or would you like to take 10 minutes to wrap your mind around the next two within your small groups? No? You just want me to tell you?
Not tell it.
Well, which one?
But walk through it like that?
Yeah.
Okay. Just for the sake of time, I'll do that because I would like to get to how we use this for solving. So, the base raised to a power of 1 rule says that any number raised to a power of 1 is equal to the base. So write an exponential equation to represent this rule. B is the base. So b raised to the what? 1. There's by the way, I went back to number 2. B raised to the first is equal to b. Can I erase this word here? Okay. So write your exponential equation from part A in logarithmic form. Is that a true statement? Because what's the exponent that would go on the base here to get b? The exponent would be 1. So state this logarithmic relationship in words. We did b to the 0 equals 1. Not b to the first equals b. We didn't do number 2, we did number 1.
That was all for number 1. Strong arrow.
Yeah, show them being switched. Okay, so any logarithm where what? This is again called my what?
The argument.
The argument.
Where the base and the whatever.
When the base and the argument are the same, the logarithm equals 1. Okay? So any logarithm where the base and the argument are the same, the log equals 1, right? And another way to say that is the logarithm or the exponent equals 1.
Yeah, I said log base b of b is always 1.
Yeah, but that's closer to this algebraic representation rather than using words to describe it. Does that make sense? Okay, so here's number 4. So write a sentence to summarize the quotient rule of powers. We should be able to use the product rule of powers to help us a good bit here. When what? No, subtraction's on the right hand side. That's what happens at the end. Why did we end up subtracting? Okay, so when dividing powers, it's got to be with the same base, right? With the same base, subtract the exponents.
What if it's not the same thing?
Then you can't do it.
Is it gonna still be an equation, like, I mean, it's still gonna be
You
a
can
Then what do you do?
3 to the 5th divided by 2 to the 3rd.
But what you gonna do with it?
Well, I can't use any of the power rules. I mean, I can still evaluate 243 divided by 8.
Oh,
Like, I can't use a power rule. And that's the thing you gotta remember, the bases have to be the same.
okay.
To use a power rule, I can still evaluate, but if I had x to the 5th divided by y to the 3rd, I can't do anything. It's gotta stay like that. Okay? That's a good question, but yeah. Okay? And so instead of going